Have you ever noticed how some things don't just grow? They seem to explode? Like a viral video, or maybe the interest on a credit card. It's not this slow, steady climb. Nope, it's a rocket launch. And that kind of explosive change, well, it follows a very specific mathematical pattern. Today, we're going to unlock the code behind it, exponential equations. Okay, so let's just jump right in with a question that seems kind of weird at first. What could a booming town and a car that's losing value possibly have in common? I mean, one's going through the roof, the other's plummeting. They feel like total opposites, right? But what if I told you they're just two sides of the very same mathematical coin? And here it is. This is the secret. Just look at the shape of those graphs. It's the same fundamental curve, isn't it? Just one is the mirror image of the other. This J-curve is the visual signature of exponential change. That moment where things start off kind of slow, and then suddenly, whoosh, they just dramatically accelerate up or down. So this curve, it has a name, and more importantly, it has a formula. To really get how this works, we need to pop the hood and look at the mathematical engine that's driving all this incredible change. So let's break it down. This right here, this is our master key. Y equals A times B to the power of X. It's just three little letters, but man, do they pack a punch. A is just our starting point. That's easy enough. Think of it as the initial population of our town or the car's original price tag. But B, the base, that is the magic number. It's the multiplier that decides the entire story. And here's how simple it is. It all comes down to what B is. If B is anything greater than 1, bam, you get that rocket launch, that explosive growth. But if B is a fraction, something between 0 and 1, you get decay. The curve just takes a nosedive. It's that simple. One number tells you if you're going up or down. All right, theory is great and all, but let's see this thing in action. We're going to model growth with a real-world example. This is where the math really comes to life. So how do we get that B value when something is growing? Well, it's actually pretty intuitive. We start with 1, which represents 100% of whatever we started with, right? Then we just add our growth rate, which we call R. So if you have a 3% growth rate, our B value becomes 1.03. We're keeping everything we had, plus that little extra. That simple addition becomes our engine for growth. Okay, let's put this tool to work. We've got a small town, starts with a population of 1,000 people, and it's growing at a nice steady 3% every year. The big question is, what's the population going to be in 5 years? Okay, let's just plug in the numbers. Our starting amount, A, is 1,000. The growth rate, R, is 3%, which we write as the decimal 0.03, and the time, T, is 5 years. We just slot those numbers right into our formula, so we get 1,000 times 1 plus 0.03, all raised to the power of 5. And when you calculate that out, after 5 years, the town's population is predicted to be 1,159 people, if we round it off. That's the power of compounding growth, captured perfectly in one little calculation. Pretty cool, right? Okay, so we've seen the curve shoot up, but what about when it goes down? Well, the beautiful thing is, it's the exact same logic, just flipped in reverse. Let's model some decay. Let's use a common and, well, sometimes kind of painful example. A brand new car that cost $45,000. But the second you drive it off the lot, it starts losing 20% of its value every single year. So how much is it going to be worth after those same 5 years? So the process is almost identical. We find our A, our R, and our T. But here is the one absolutely crucial change. Instead of adding the rate, we subtract it. Our decay factor becomes 1 minus 0.20, which is 0.8. And since that number is less than 1, we know we're on the right track for decay. Punch that into a calculator and wow. After 5 years, that $45,000 car is now worth just a little over $14,700. It's a pretty stark reminder of just how powerful exponential decay can be. So far, we've been solving for the what. What will the population be? What will the car be worth? But honestly, a lot of the time, the more interesting question is when. How long is it going to take for something to happen? And to answer that, we need a new tool in our toolbox. Let's stick with our poor, depreciating car for a minute. We know its value is falling fast, but when exactly will it hit a specific target? Let's say, when will it be worth only $3,000? So when we set up this equation, we kind of hit a brick wall. The variable we need to find, t for time,
is stuck up there in the exponent. You can't just divide or subtract to get it down. It's totally trapped.
So how in the world do we free our trapped variable? We need a special key, one designed specifically to unlock exponents, and that key has a name. It's a logarithm. The best way to think about it is this. Just like subtraction undoes addition, a logarithm undoes an exponent. It's literally the undo button we've been looking for. And the method is a really clear four-step process. First, you've got to get the part with the exponent all by itself. Then, we use our special key. We take the logarithm of both sides of the equation. This is what lets us do the really cool part in the next step. And this is the magic trick. There's this awesome feature of logarithms called the power property. And it lets us take that variable t from way up in the exponent and just bring it down in front as a regular old multiplier. Just like that, our variable is free, and the equation becomes simple algebra we can actually solve. From here, we just divide both sides by the log of 0.8 and we get our answer. It's going to take about 12.1 years for that car's value to drop all the way down to $3,000, and there's no way we could have answered that how long question without our new tool, logarithms. Okay, so we've solved for a growing town, and we've solved for a shrinking car value. But this is so much more than just a math exercise. Why does understanding this curve, this formula, actually matter in your life? Because this isn't just some abstract math from a textbook. This is the language of our world. It's how your savings grow with compound interest. It's how scientists date ancient artifacts using radioactive half-life. It's how bacteria multiply, how asset values change, and it's even how we measure the sheer power of earthquakes. This math is literally everywhere you look. So I'll leave you with this question to think about. Look around your own life, your savings account, maybe your career progress, even learning a new skill. What's following that same powerful curve? Because once you see it, you really can't unsee it. The math is now yours to use.